All right, these are the answers to the exponential growth decay worksheet. And for the first one, it says Wendy's bank account is increasing by 3%. So when we do see that percent increase, decrease, what we always want to do is start with 100%. That's what we currently have. And we're increasing by 3%. So we're going to add 3% to that. So that means next year, we'll have 103% of what we have right now. And if we change that to a decimal, that's 1.03. That's what we're going to call our multiplier. Okay? So if I have what I currently have and I multiply it by 1.03, that'll tell me what I'll have next year. Do it again, that'll tell me what I have the year next year and the next year and the next year. So when I create an equation for this, I'm going to take what I started with, which is 2,500. All right, so that's our starting amount. And then I multiply it by this 1.03. For us, that's our multiplier. And then this creates a generic equation then. If I want to know what it's going to be in 10 years, I just put 10 in for t. When I want to know what it was 5 years ago, I put -5 in for t. This formula will help me go backwards, forwards, and find out what the amount of this is at any point in time. So when this says how much will be in 4 years, I just go ahead and take my calculator, all right, and I type in 2500 times 1.03 to the 4th power, and it gives me 2813.77. So we're getting, we're putting 4 in for this. So again, what we're doing is going 2,500 times 1.03 to the 4th power, and that ends up giving us our answer. For number 2, it says the value of Ted's car is decreasing by 11%. Decreasing by 11%. So I start with 100%. Decreasing means I'm going to subtract 11%, and it gives me 89%. Move that decimal 2 spots, and here's my multiplier, 0.89. Okay? The current value is 9,000. So when we make our equation, current value, 9,000 times 0.89 to the t power. So there's our formula for that. Okay? So then how much will it be worth in 8 years? We're going to go 9,000 times 0.89 to the 8th power. All right, so I take my calculator and go 9,000 times 0.89 to the 8th power, enter, and I get 3542.93. $3,542.93. That's how much this car would be worth in 8 years from now. So that's creating the equations, using them to do this type of thing. Right? Hopefully that feels pretty good. Now we're going to have a situation where the equation's given to us. This says the population of a city has been changing since the year 2000, and here's the way that it's been changing. And we can see that we have this 1.04, that's our multiplier. So if I were to take that 1.04 and go backwards, let me move that decimal point 2 places. That would be 104%, and that would be 100% what you currently have, and to get to 104 we would have to add 4%. So that's going to be key here in just a second. So I took the multiplier, changed it back to a percent, broke it into 100%, and then either plus or minus whatever we're dealing with. So is this an example of growth or decay? Well, we're adding percentage, so this would be growth. Again, because we are adding a percent, we're going to say it's growth. What's the percent the population is increasing or decreasing by? It's increasing by 4%. What was the population in 2020? So now we're just going to use the equation they give us. All right, we don't really have to do anything else to it. We're just going to put it into our calculator. We're going to go 35000 times 1.04 to the, now this is from the year 2000, so 2020 would be 20 years later. We're going to put 20 in for t, And so again, I went 35,000 times 1.04 to the 20th power, and I got 76,689. We'll round that off to the nearest person. In what year was the population of the city more than 40,000? So what I want to do is I want to take my equation here, and I want to just kind of keep playing around with the exponent until I get something bigger than 40,000. So I can, with this calculator, I can just go up and hit enter, and then I can just go ahead and change this. So let me say, what about if it was 10 years? If I hit enter, well, that's more than 40,000. Let me try something sooner than that. Let me try 5 years. All right, now we're real close. It's 42,582. All right, let me try 4 years. All right, 4 years is more than it. And what about 3 years? And 3 years is less. So you can see that between 3 and 4 years, we flipped from less than 40 to over 40. So in what year was the population city more than, so it would have been between 2003, 2004. Somewhere in that range is when this town jumped over the 40,000 mark. Okay? And it was just through some trial and error. I just kept playing around with numbers until I made it work. All right, so same thing here. This one says population of deer at Grant Park has been changing since the year 2010. Scientists used census data from, should be 2010, to create the model, okay? And so I see this 0.98. And I'm gonna take that 0.98, I'm gonna change it into a percentage. If you move that over, it should be 98%. Now, again, I wanna refer to that in terms of 100%. So 98% is 100% minus 2%. So again, that minus 2% is gonna be important here. Is this an example of growth or decay? Because I subtracted, this is decay, okay? What percent did it increase or decrease by? 2%. So being able to take that 0.98, rewrite it as a percentage, and then put it in terms of 100%, that'll tell you whether it's growth or decay and by how much. All right? And then the last thing is, what's the population in the year 2015? So this is since 2010. So 2015 would be 5 years. So I'm going to take my equation here, 350 times 0.98 to the 5th power. And if I round to the nearest deer, I get 316. Again, that's 350 times 0.98 to the 5th power. Gives us that.